Saxon Advanced Algebra, lesson 77. This is a fun one. It's called Binomial Expansion. That's a fancy name for a relatively straightforward idea. There's a fair amount of upfront explanation I need to do in this lesson, but there are two examples once we get into it. All right, what we're starting with is the basic idea of a binomial. There's a binomial, and very often we have seen, we've been asked to square binomials, right? And we know there's a pattern. There's going to be a squared term, and then there's going to be a combined term, and then there's going to be another squared term, isn't there? We could get these by multiplying. Let's just do it. I'll do it on a separate piece of paper because I know just how this one needs to look. We can multiply these. We call it the dance, right? There's no numbers here. We're doing it with all letters. This would be a squared. This would be AB. She's done. She sits down. Her term. We get another AB. And then we get a B squared term. Add them together. And that's what we get. I'm going to copy this onto the next page. But what I'm going to do is I forgot the 2. That's important. I'm going to give these coefficients, or these terms, a coefficient of 1. And I'm going to give these guys exponents of 1 so that everybody's got a coefficient and everybody's got an exponent. All right, so this is what is going to go here. Beautiful, okay? Now let's go back. Let's take the simple version of this. It was a squared plus 2ab plus b squared. We don't need the ones. And let's multiply it one more time because what we want to calculate, we're going to multiply it by a plus b again. Okay, that's the end of that. And then we'll come up with the binomial a plus b cubed. All right, so we just multiply. I multiplied all the way through on this. I'm hoping you're multiplying too and just following along. I'll slow down a little bit since this is a little less familiar. A cubed, 2a squared b, ab squared. She's done her term. Now we have to be careful to line these terms up. This is a squared b. This is 2ab squared, and then this is b cubed, all right? Not difficult, just have to be careful when we're doing these. And look at this big long thing that we get. It's got a kind of pleasing pattern, right? It's got the cubed and the cubed, and then it's got a 3 and a 3. The square changes from the a to the b. And we're going to do the same thing. We're going to put coefficients of 1 here, and then any exponent that doesn't, or any base that doesn't have an exponent will give a 1 too. All right, now I'm going to copy this onto this list I'm making on the other page. And you'll see I'm writing this in a very specific way. You'll understand. So this is just my answer. I'm writing it down. Make sure you're writing this as well. Try to get these, I'm trying to center these in the middle of the page. Okay. Now we're going to go on and we're going to find a to the 4th and a to the 5th, but let's go up first. A plus b to the 1 power. Well, that's just a plus b, isn't it? But we'll do the same thing. We'll give it a 1 and a 1, right? Coefficient and an exponent. And then let's just go one better and do a plus b to the 0 power. Anything raised to the 0 power is 1. Okay, so you can see that as we raise the power of the binomial, we're getting a kind of triangular effect. We keep getting more and more terms. We're going to add a plus b to the fourth to our concoction, and then we'll do a plus b to the fifth. That one will kind of squeeze in as well. Okay, so we could calculate it. We could keep multiplying by a plus b. Each answer that we get, just multiply it by a plus b. But I'm tired of that, so let's just use notes. There's the product we would get if we multiplied a plus b quantity together 4 times, right? We would take this and multiply it by one more time. And then let's add this one. That's an A. Always the A and then the B. All right, I'm just double checking to make sure I didn't make any crazy mistakes in this. Okay, what you'll notice is that as we go we take our binomial, and as we increase the exponent, we get more and more terms, right? But they follow a very specific pattern. So we're going to look at those 2 patterns. The first thing we want to look at is the pattern that the exponents make. All right? Let's take just one of these rows. Let's take the biggest row. Quantity a plus b to the fifth, right? And I'm going to copy the exponents, but I'm going to write them just a little differently. For the first term, we can write a to the fifth, b to the 0. Right? We can put that in. B to the 0 is always 1, so it doesn't change this value. Now let's look at the next term. It is a to the fourth, b to the 1. I'm just copying now because this is all exactly the way I want it. Oh, that's not a plus. Okay, I'll give you a second to copy that. And again, this is not anything new. I'm just taking these exponents. I'm ignoring the coefficients. I'm writing the exponents. And for these 2 end terms, oh, this should be a B. I'm sorry. For these 2 end terms, I'm adding in the other term to the 0 power, right? Because here there's no B, here there's no A. So I'm adding them. Now, let's look at what's happening to the exponents on the A term and the exponents on the B term. Here we have 5 and 0, right? I'm just copying these this way. 4 and 1. On our first variable, our first term in the binomial, notice that we're starting at the highest power, right? Because we're raising this to the 5th. We start with the 5 and then we go down. With each additional term, the exponent on the A drops until it gets all the way to 0 in the last term. Notice that with the B term, it starts at 0 and it climbs. That is a really cool and interesting pattern. Super easy to replicate, right? Notice that this is to the 5th power, but there are 1, 2, 3, 4, 5, 6 terms. So the number of terms is always going to be 1 greater than the exponent. So this gives us a really easy way. If we want to find the exponents on any particular term of any particular power, we can easily reproduce this kind of a chart. After a few minutes, you'll be able to do this. You'll be able to skip in and just figure out which one it is fairly easily. But we can always write out this pattern and be able to calculate the exponent on any power, right? It doesn't have to be on our chart. We could take a plus b quantity to the 15th, and we could write out the pattern of exponents and be good to go. Okay, so what about the pattern of the coefficients? That's the other piece of this puzzle. There was a dude named Pascal. Let me see if it says what year he did this. I think he was a European dude. I think he was like 1600s, 1700s, maybe even the 1800s, somewhere in there. He studied this and he realized that these coefficients make a really neat pattern. And that pattern is called Pascal's triangle. And I'm going to use a secondary piece of paper again so that we can look at this but have room to write as well. So here comes that. I'm ripping off the little edge piece of a piece of notebook paper. Okay, so what I'm going to do here is I'm going to copy, now I'm ignoring the a's and the b's and their exponents. I'm just looking at the lead coefficients. 1, 1, 1, 1, 2, 1. This is why I did the triangle shape to this. It'll all become clear in just a second. Just copying these numbers. 1, 4, 6, 4, 1. 1, 4, 6, 4, 1. And then our last row, 1, 5, 10, 10, 5, 1. 1, 5, 10, 10, 5, 1. And then I'm just going to put the exponent in a column over here. This was to the 0 power, the first power, the second power, the third power, fourth power, fifth power. And I'm going to put a little box around these just so that they don't get confused with our triangle. This is the exponent that we put on the quantity a plus b. Okay. So again, these I'm just pulling off of our chart, but what I'm going to do is I'm going to teach you how to reproduce Pascal's triangle by yourself really easily. It starts with a 1. That's pretty easy. Then there are 2 1s. Okay, that's really easy. Once you get the first 2 rows in, what you do is you begin to add. We always add 1s along the outside, and these numbers add up. You see what I mean? 1 plus 1 is 2. The number that's sitting halfway in between these 2 1s is a 2. Here's a 1 and a 2. There's the 3. The 3 and the 3, oh look, there's a 6. 6 and 4, 10. So it's very easy to reproduce this. We put a 1, then we put 2 1s, then we start adding in the middle and adding 1s on the outside. So we can very easily reproduce this triangle. I'm going to do it again, and this time I'm just going to walk through the talking of it. There's my 1. There's my 2. Now I do 1, 2, 1. That came from that. Then I do 1. There's a 3. There's another 3. 1 on the outside. Here's a 4 and a 6 and a 4 and a 1. 1 on the outside. 5, 10, 10, 5, 1. So you see, to create Pascal's triangle, we can very easily just keep layering in the 1s and adding to get the middle terms. We know that the exponents there's always one more term than it is an exponent. So here we have one term, there's a 0. When we have 1 on the exponent, we have 2 terms. When we have 2 as the exponent, we have 3 terms. 3 as the exponent, we have 4 terms. So remember that, here's the 5. Remember that the number of terms does not equal the exponent. The number of terms is always one more than the exponent. We can recreate the coefficients using Pascal's triangle. And we can recreate the exponents using this simple pattern. That makes it very easy for us to come up with crazy high expansions of this basic binomial without having to do this till we're blue in the face. Look, we were only up to a plus b to the 3rd power. That's not very high, and it was already so annoying. So the combination of this exponent pattern and Pascal's triangle allows us to expand binomials without having to do it by hand. I love it. How do we do this in a problem? Very straightforward. Write the 4th term of x plus y quantity to the 6th. Okay, let's do the pattern of the exponents first. We know that there are going to be 7 terms, so what I'm going to do is I'm going to write a and b. These are the exponents would be on them. In the first term, if we're raising it to the 6th power, a is going to have a 6. Then it's going to go down with every expansion, right? And there we know we should have 7 terms. 1, 2, 3, 4, 5, 6, 7. Perfect. Now we know that the b is going up. Again, this is where we're talking about the exponents on each term. We want the 4th term. So we simply toggle down. This is the one we're interested in. Okay? So we know that in our answer, I'll put the answer way down here so we have plenty of space because we have Pascal's triangle yet to create. We know that it's going to be x cubed y cubed. This isn't right. We're not using a and b in this example. We're using x and y. All right. So we know that these are the exponents that are going to sit on our 2 variables. Now we need to recreate enough of Pascal's triangle to get to where we are. Let's do it from scratch, even though I could grab my notes. The 0 term, raising it to the 0 power is 1. Okay, so this is the 0 power. This is the 1st power. 2nd power, put a 1 on the outside, add these two. 1, oh, I skipped his line there. 3rd power, 1, 3, 3, 1. 4th power, 1, 4, 6, 4, 1 on the outside. Oh, we have to go up to the 6th power. I'm running out of room. 5, 1. 1 and 4 is 5. 6 and 4 is 10. 6 and 4 is 10. 4 and 1 is 5. And then 1 on the outside. Okay, here it comes. Here's our glory run. Squeezing 1, 6, 15, 20, 15, 6, 1. You notice we always get this nice symmetrical pattern, right? Either there's a middle number and then it matches, or if there's an even number of terms, then we have the same thing twice in a row, right? Okay, so we are looking for the 4th term of the 6th power. Here's the 6th power, 1, 2, 3, 4. So this is our coefficient. And there it is. There's the 4th power of quantity x plus y to the 6th. We did not have to do any multiplication. We just used our 2 patterns for the exponents and the coefficients. This is called Pascal's triangle, and we got the right answer. One more. 27.2. Write all 8 terms of the expansion quantity x plus y to the 7th. So this time John's asking us not to just zero in and do 1. He's asking us to find the whole row. All right, let's do the exponents first. We're using x and y. 7th power, so we know that the x is going to start with 7. And then the y is going to start with 0 and go up. Oh, there was one other thing I wanted to show you about this. I forgot to tell you before. When you lay out these exponents, you'll notice that if you add them together, they should always add to the power out here. See how that works if I add them up? That's another great way to double check to make sure you haven't made some silly little mistake in your arithmetic. The 2 exponents together should always add to 7. Okay, now we have to do Pascal's triangle all the way up to the 7th power. Let's torture ourselves by starting over. Right, I'm just adding to get the middle ones. Actually, you should ignore me and try doing this on your own. And I do want you to practice. I want you to practice recreating this every time. I know it's kind of a pain in that you've already written it down and you can just look at that, but this will remind you of, this will train you how to actually do it. It's not hard to do. Obviously, I'm just adding up numbers and putting ones on the outside. But just to make sure you get the hang of it, please do it a few times. Okay, 0 power, 1, 2, 3, 4, 5. I have 2 more rows to do. Zero, 1, 2, 3, 4, 5, 6. Okay, here comes our glory lap. 1, 7. Look at how hideously large these coefficients have become. But if I did it right, I should get that really pleasing pattern. 7th power, I should have 8 terms. That means there's going to be 4 and 4. And I see, look, it stays perfectly balanced, right? 1, 7, 21, 35. And then I turn around and go the other way. 35, 21, 7, 1. Beautiful. So now I'm going to combine this row and this information to write out those terms. So here we go. It's going to take me 2 rows to do it because there's so many. We will say the first one, the first term is x to the 7, y to the 0. The second term is 7, x to the 6th, y to the 1, plus 21. This is my third term, so I'm here. X to the 5th, y squared. Okay, I'm just continuing. Plus 35. This is my first 35. I'm on term 4. X to the 4th, y to the 3rd, plus now the second 35. And there are my exponents. Plus, now I'm at the 21, right? I'm on the 1, 2, 3, 4, 5, 6th term. 1, 2, 3, 4, 5. Okay, good. 21. X squared, y to the 5th, right there, plus 7, x to the 1st, y to the 6th, plus my last one, 1, x to the 0, y to the 7th. That's my answer. Now, obviously, I could simplify some of these. Like this, I could just write, this whole term I could write as x to the 7th power, and this one I could write as y to the 7th power. I could drop this one, and I could drop that one. But it's okay to leave them in, just because that helps us manage our patterns better. This is our final answer. I hope I didn't make any ridiculous mistakes in there. That's a lot of details to keep straight. But I'm sure you will agree, this and this are much faster ways than multiplying this ridiculous binomial times itself 7 times. That would make me want to cry. All right, Pascal's triangle, the pattern of exponents. You are locked and loaded for lesson 77. Thank you. Goodbye.